Solving systems of equations. In the past, we've basically done systems of equations with linears, meaning x, y, both of them to the first degree. So linear equations, and they give you examples, x, y, even x, y, z, all to the first degree. These are linear equations. And then we have nonlinear. You notice the difference here. My variables go up, x squared, y squared, or you multiply the two variables. X, y is not linear as well. X cubed, not linear. So once your degrees go up, or you multiply those variables side by side, you go from linear to nonlinear. Solutions. Is it a solution? If you have a point and you want to know if it's a solution, you literally just plug it in, okay? Plug it in. Does it give you a true statement? If it gives you a true statement, then it is a solution. If it doesn't give you a true statement, it is not a solution, all right? So, same process, whether it's linear or not. They just gave us an example of linear, all right? Substitution. If you have the answer, substitute it in and figure it out. If you don't have the answer, one of the ways you can solve is substitution, all right? And so, like I said, we've done this before. If you're solving by substitution, you want to get a variable by itself. You want to plug it into the other guy, and then you want to solve based on one variable because you're not going to be able to solve with two variables. I always pick the path of least resistance, all right? I look for the variable that's the easiest to get by itself. You have two options here. The first one has a y kind of by itself, but we have a negative. That negative is going to give you more room for error, all right? Negatives do that. So I would actually set the second guy with a variable by itself. I would take that x plus 3y, and I would move that 3y over. That gives me x equals negative 3y minus 3. Once I do that, I am going to take that whole group and I am going to plug it into the other equation in place of x, the guy that I got by itself. So I'm going to rewrite this first one. I'm going to say 2 instead of x. I'm going to write what x equals. Then minus y equals 8. And I have a basic, this is something we could have done in Algebra 1 equation to solve, right? My first step is to distribute here. Minus y equals 8. Combine my like terms. So I have negative 7y minus 6 equals 8. Add that guy over. So add my 6 over. Negative 7y equals 14. So y equals negative 2. All right? When you're solving a systems of equations, you are not done until you know what all the variables are. I only know one of the variables. Once I know one, I can plug it in to solve for the other. So I can just throw that right up there. To solve for x, negative 3 times negative 2 minus 3. I'm going to get positive 6 minus 3. X is going to equal positive 3. So my answer here will be positive 3, negative 2. Solving by substitution. All right, so you can also do substitution with nonlinear. Something like this would be a nonlinear systems of equations. One's going to be linear, one's going to be nonlinear. So the dimensions of a rectangle whose perimeter is 48 feet, whose area is 108 feet. If you need to get a visual, draw a rectangle. Easy enough, right? So if I were to do this, I would say, well, I have an x and y. That's my dimensions, okay? They want me to tell what those are. Perimeter, so they've given me 1. Perimeter is going to be 2x plus 2y, and that's going to equal 48. They give me a second one, area. Well, area is going to be x times y, and that's going to equal 108. All right? So you can see how we're going to do substitution here. There's actually two ways to do it. You can do substitution by dividing one of them over, right, on that second one, or you can do substitution by subtracting the first one. I would also say simplify while you can. So if I have 2x, 2y, and 48, I can divide everything by 2. And so I always reduce when possible. Smaller numbers makes fewer errors. So I have x plus y equals 24. And I would likely do my linear, set that one equal to one of my variables, and then plug that into my nonlinear is what I would do here. So if you were to subtract your y over, you would get that x equals, they actually did it the other way, that's okay, x equals 24 minus y. Or you could do the y, set the y equal, and you would say y equals 24 minus x, right? Either one of those. And then plug it into the other guy. All right, plug it into the other guy. If I were to take this one and plug it in, I'm going to replace the x, right? So I'm going to say instead of x, I'm going to say 24 minus y times y, and that equals 108, right? Distribute, so I get 24y minus y squared equals 108. When I have, this is a quadratic, anything squared, any polynomial really, the first thing you're going to do is set it equal to 0 and figure out if you can factor it. So I always make sure, by the way, when I set it equal to 0, that my leading coefficient's positive. You're going to mess up your factoring if your leading coefficient is negative, always. So either divide out a negative or move it over where you definitely have a positive. So you're going to move it over. That's going to be a positive y squared, a negative 24y, and a positive 108 equal to 0. That actually does factor. It's not an easy factoring, but it does factor. 6 and 18. So 60 and 48. Yeah, so that's 108. So this will factor to y minus 6, y minus 18. Y is going to equal 6 and 18, which actually are your dimensions. Because if you were to plug that back in to here, if you plug in an 18, you're going to get 6. If you plug in a 6, you're going to get 18. Your dimensions are 6 and 18. So it's going to be 6 feet by 18 feet. Those are my dimensions. And you can check it. Would that give you a perimeter of 48? Would that give you an area of 108? You can double check it. So with linear systems of equations, when we only did 2 lines, it's only possible to either have one answer, no answers, or they're the same exact line. Okay, that's really your options there, right? But when you're talking about nonlinear, you can talk about curves. So xy is actually going to be a curve, which means it could cross a line more than once. All right, you're really looking for where these two have the same answer that makes them both true. So let's say we had a parabola and we had a line. So if we have a parabola and a line, you can have 2 answers. You could have more than 2 answers. You could have, we've seen them that bounce up and down, and then a line could go through it, right? So it's not necessarily, hey, I only have one answer here, like we did on our dimensions question. It's possible when you're talking about a nonlinear and a linear that line crosses more than once, just depending on what shape of the nonlinear that you have. If it were 2 linears, lines can only cross at most at one point in Euclidean geometry, right? So again, this should be familiar. Another thing that it is called is solving by addition, right? But eliminations means I'm going to look for the easiest variable to eliminate. I may need to multiply to do that. I need one variable to have a positive and negative of the same coefficient. All right, so I look for the easiest positive and negative. I already have y's that are positive and negative, and they're smaller numbers with a smaller common multiple. So I would eliminate my y's here. I'm going to multiply my top one by 2. That means every single thing gets multiplied by 2 there. I'm going to multiply the bottom one by 5. Again, every single thing gets multiplied by that 5. And so when I do that, my top equation goes to 12x minus 10y equals negative 86. My bottom equation goes to 35x plus 10y equals negative 55. And then because it is called elimination, but it's called addition typically because you add down, that will eliminate that variable. That's your whole goal, eliminate a variable. We have 12 and 35 gives us 47. 86 and 55 gives us 141. That's actually perfectly divisible by 3. So 120 and 21 give us 141. So when we divide 141 by 47, we get x equals, that's a negative 3 because it's negative divided by a positive. Once you have one, plug it into either equation. It doesn't matter which, and you can solve for your other answer. So I have my x, I have my y, negative 3, positive 5 is my answer. I can always check these, plug your x and y in, see if it works for both of them, just like we did with the rectangle. Does it give you the answers that it said it would give you? This says use technology to solve the system graphically. It says technology because you're not going to perfectly graph a log function. You might be able to sketch it, right? But you're not going to perfectly graph it. And so you can do graphing technology, which is where you can see that you could have potentially more than one answer. If you look in your book, you're going to see you have your log graph and you have your parabola. So your log is going to shoot off to the right there. Your parabola is going to be what every parabola looks like pretty much. And then you can use your graphing to figure out exactly where they cross, where those two cross. We're not going to do any sketching right now or any graphing, but we will later on. And so this is one of the methods that we have used in the past with linears. We've solved by graphing, right? And you can, it's much easier if you have a linear and a parabola, something like that. You could sketch those pretty simply. But logs are not going to be exact when you sketch them. Like you're not even going to be able to exactly pair those up because you have so many that are, as this one's going to be rounded. Okay, and so if you have a rounded answer with a log, you're probably not going to be able to find that on a graph unless you use technology, some sort of either app or your graphing calculator to do it. So we're not going to do that right now, but we will later on. Types of linear systems specifically, we've talked about this in the past. Classification, independent and consistent. That means there's only one solution, those two lines intersect. Dependent and consistent. There is an infinite number of solutions. It means they are the same line, right? When you end up setting them, if you get them in slope-intercept form, for example, it'll be the same exact line. And the last way is inconsistent. You have no solution, the lines are parallel. All right, so those are your options when it comes to linear. That's only linear. Depending on what you have, it may be that you solve them different ways. So remember I said solving by elimination is almost always the way that I use to solve things, right? I say almost because if you look at this first one, I'm not solving by elimination here. Not. First, it's already set up beautifully for substitution. Second of all, I can see that when I substitute in, I actually get rid of that variable because the coefficient is the denominator, right? And so why am I going to solve by elimination using fractions when plugging it in will get rid of my fraction, right? And so this first one is set up beautifully for substitution. I would use substitution here and solve. The second one I'd be solving by elimination because I can really just divide that second one by -2, divide everything by -2 actually, and it's already set for me to eliminate. And so being able to see quickly, hey, one method or the other is probably going to work better is going to do you well, because most of the time I'm not going to say solve it by this way, solve it by that way. At this point, I'm just going to say solve. All right. And when you get a standardized test and they say solve this system, it's not going to remind you that you can solve by elimination or to solve by substitution. It's just going to want you to come up with a method to solve the system. And so recognizing the easiest method to do is beneficial. So for this first one, I would substitute. I would take this little guy here and I would plug it in for y. For this one, I would divide everything by -2, right? Because two things, I'm making my number smaller. Second, I have a 3x and a -3x at that point. So, and this is actually going to be, and this, once you do that, you're going to see you zero everything out and you're going to get a special case anyway. All right. If you get a false statement, so like for this one, 3x minus 4y equals -8. What happens here? 6 divided by -2, -3x, -8 divided by 2, positive 4y, 12 divided by -2, -6. When I add that down, what happens? These eliminate, which means I have 0 equals -14. That is a false statement. That's going to be no solution. That's going to be inconsistent, right? So you want to also, that's a very quick check, right? And so you want to look for special cases as well. A phone manufacturer has determined the supply and demand curves for a cell phone, where P is the price in dollars and X is the supply in thousands of phones. For supply, we have P, or the price, equals 400 plus 0.8x. For demand, we have P equals 1,000 minus 0.4x. Find the equilibrium price and the number of phones that should be produced. All they're saying is find the price point that meets both of those, and then how many phones. So they're really asking you to find your P and your X. That's all they're asking for, all right? This guy is set up beautifully for which type? Substitution or elimination? You can really do either here, right? You could do either here. Substitution, I would just set each of those equal to each other. All right, so if I have P equals something, P equals something, if I were solving by substitution, I would say, oh, well, this P, the 400 plus the 0.8x equals that P, the 1,000 minus the 0.4x, right? That's substitution. If you wanted to do elimination, you could have multiplied the bottom guy by 2, right? You could have said 2P, 2,000 minus 0.8x, right? And then you could have solved for P. So either way, this is actually set up pretty nicely to do either method, depending on which one you like. Since we already have this one set up, subtract my 400 over here. That's going to give me 600. Add my 0.4 over here. I think that's how they did that here. So 1.2x, and then divide both sides by 1.2. You're going to get x equals 500. In the problem, they told me what that was. What was x? This is my number of phones in thousands, right? X is the supply of phones in thousands. So when they say how many phones should be produced, I've already solved that guy. The number of phones is 500,000, right? 500,000 phones. All right. We don't plug in 500,000, by the way, because they've already told me that it's in thousands. So if I'm going to solve for my P, just plug in a 500. All right. So we can take either one of those equations. To solve for P, we just plug in our 500. 400 plus 0.8 times 500 is going to give me a P equals 800 phones. 0.5 times 500 is 400. 400 and 400 is 800. So 500,000 phones with a price of $800. All right, I always solve three variable by elimination. There is a method to solve by substitution. So I, again, look for the path of least resistance. I often look for one that has one variable. So like X here, probably be easy to eliminate. You could eliminate Y, but when I look at this, you're gonna have to multiply this guy by 5, which makes for bigger numbers, right? So I would probably use my X to eliminate. Remember, to eliminate, you take 2 of them, and then you have to take 2 different ones to eliminate the same variable. We're trying to get it down to a 2 variable. That's what we're trying to do. So I would take these 2 here, these first 2, and I would use elimination, multiplying the first guy by 2. All right, so multiply the entire first guy by 2. That gives us a negative. I'm gonna have to move over because I'm gonna run out of room. Negative 4x, positive 10y, positive 4z, and positive 46. Don't touch the second guy. Leave him alone. All right, and then we're just gonna add down like we did before, okay? So we're going to add these 2. All right, so we have negative 4x and positive 4x cancel. Positive 10y, negative 1y gives us 9y. Positive 4 and positive 2 gives us 6z. And 46 and negative 13 gives us 33. All right. All right. Then you have to take 2 different ones. All right. So if I were to do 2 different ones, I would probably do the first one and the third one, right? Because I already have a negative and a positive as well. And then I would multiply that third one by 2. So leave the first one alone here. Negative 2x plus 5y plus 2z equals 23. Multiply the bottom guy by 2. Positive 2x, negative 6y, positive 12z, and negative 34. Add those up. Again, my x's cancel, which is really the whole goal here. Negative y, positive 14z, negative 11. All right. Then I created a couple ugly ones. Maybe that's why they did it the other way. So I have two variable. That's what you're looking for. And by the way, if you ever have one that already has a variable eliminated, use the other 2 to eliminate that variable. Easy enough, all right? All right, so actually, what can I do with that first one? There we go. So divide everything by 3. 2 and 11. Oh, much better. All right, so I can multiply the bottom guy by 3 now, so leave the top guy alone. 3y plus 2z equals 11. Multiply this by 3, negative 3y, 30 and 12, 42. All right. Hopefully y ends up being pretty. All right, again, he cancels. This is 44. 44 is z, and this guy's going to be what, 22? So z is going to be 1/2. Yes? Negative 1/2, technically, since he's negative. All right. Then you work your way back up. All right. I will say z is going to be pretty because he's actually going to cancel out when you plug him in. So no matter which one you plug him into, whether it's this one or this one, that denominator is going to cancel. Once you have 1, you just work backwards, okay? I take this negative 1/2, plug it in. So 3 times y plus 2 times negative 1/2 equals 11. So 3 times y minus 1 equals 11. Add 1, divide by 3, y is going to equal 4. So now I have 2. And then you're going to work your way back up to the top. Again, it doesn't matter which one. That 1/2 is going to cancel from any of the z's that you plug it into. So you can just take any of them. We're going to say maybe 4x minus y. We now know y is 4. Plus 2, we now know z is negative 1/2 equals negative 13. I just chose my second one. So I have 4x minus 4 minus 1 equals negative 13. Negative 5 added over negative 8. Negative 8 divided by 4, x equals negative 2. And I have all 3 of my answers. My answer is negative 2, positive 4, negative 1/2, x, y, and z.